again. So today it's Dr. Mark Platt from Loughborough University. So I met Mark relatively recently, about a year ago, a bit more maybe, when he invited me over to give a talk at the Midlands Electrochemistry Group meeting. And we have a lot in common, and it's, I think hopefully we'll find time to collaborate in the future. So it's a real pleasure to introduce Mark for his talk here today on his nanoparticle life cycle, synthesis, characterization, and sensors. So really looking forward to your talk, Mark, and over to you.
Right, well, thanks very much for the invite, and thanks to everyone who's joining us. It's I guess start off these lectures at this time to say that I hope everyone's keeping safe and engaged and enjoying the way things are going at the moment for us all in the different research environments and lifestyles that we've been placed under. It's great to be joining you from where I am at Loughborough today. If you ever are allowed back out and travelling across Europe and the UK, you're welcome to come and visit us. We're slap bang in the middle of the UK, about as far from the sea as you can get, annoyingly for our children. This is the case. And you can see that we've got quite a big open space on campus. We're famous, I guess, Loughborough as a sporting institute. We've got many cricket pitches and football pitches, but the lab is tucked away in a nice part of campus surrounded by hills. I'm clearly not coming from the lab today, as you'll see from the cameras. I'm coming from my house, but it's not a huge distance from where we normally carry out the work, and it's not a difficult commute under the best and the most typical days. I've given sort of a very vague and non-specific title, and I apologize for that, and that's because I wanted to talk about some of the different areas that we're doing. When you're young and you sort of join and you pitch your lectureship to the department, you have these great visions of doing a bit of everything, and we're still kind of doing a bit of everything because I'm still interested in all of this. I'm really going to talk about aspects 1 and 2 today in terms of some of the material synthesis and some of the flow reactors. And the idea was that I would have these interlinked subgroups that would come together and converge to build this fantastic analytical process or workflow, in that, you know, I can design materials, control their physical properties and the way they behave, and they would enhance the extraction and detection of analytes in different solutions. And the majority of the aspects I'll talk about today are using things, you know, super paramagnetic beads or magnetic beads, where we can drop them in. And in theory, the idea is that you target specific analytes in complex mixtures and you extract them, and then you couple them into some fantastic sensor technology. And if you can control all of those aspects, you can ply your hand to anything. And in some cases that's worked for us. We've done quite well in terms of playing around with different people and different companies in developing various methodologies and analytical processes, from anything from nasty biological warfare agents to radioactive radionuclides and small molecules in between. But it requires us to really understand those, and that was the concept behind the group when we set it off. And it's some of those components that I wanted to talk to you about today and give you an insight into some of the work that we're doing at Loughborough, and hopefully catch some of your interest in some of the aspects of this. And so, you know, when I came to sort of apply for an academic position at Loughborough, I was in Dublin, and we were working with these magnetic microparticles. We were doing a lot of work on synthesizing them to be able to control what they looked like and the way that they extracted from solution. And I'm sure you've all come across these before in the way that they behave. I'll go back to my, can't play the video, but the idea is that you can apply a simple handheld magnet and extract from some solution. And so in Dublin, we were playing around with emulsion droplets, where you would load those emulsion droplets up with iron oxide nanomaterials. Those emulsion droplets would be left to evaporate, they would condense down, and you'd be left with a condensed core of iron oxide nanoparticles that would respond externally to an applied magnetic field. And by going through this process, you can make them quite monodisperse, you can control the size of the emulsion droplets. In theory, you can control the evaporation rates and the loading of the material, and you can really play around with the size and some of the physical features in terms of their shapes, and then apply that to sensing methodologies. And what was interesting in the work that we were doing in Dublin is that you can obviously, if you change the shape, their drag through solution as you apply a magnetic field, changes their extraction speeds, it changes the surface area. So if you're looking to extract analytes from solution, having some control over the surface area is important, because then you can extract different amounts. And so you can play around with the surface area, you can play around the extraction velocities and how fast they move. But what's important in doing this is also to be able to understand if you're going to add a magnetic particle into solution to extract something, you want to extract all of those magnetic particles. And most of the analytical processes say that you want to do it quick, drop it in, grab hold of the analyte and extract it quickly. And not only do you need to be able to control the surface binding capacity and the speed at which they come out, but you have to have some sort of understanding of how many of these you need to add to solution. Because the number of which these particles you add to solution not only affects what you can extract, but also how quickly you can extract it. And so these are some commercially available examples of beads that you can buy. These are some examples that we can make. And if you look at the time axis here versus the fraction left in solution, not only is it about the size of the particle and the shape, but it's about how much you add. So these are all the numbers of particles per mil, and the speed at which they come out is dependent upon their concentration as well, because in the way in which they move. And we were doing a lot of work on optimizing this so that we can incorporate these into automated analytical processes that would allow us to extract the analytes of interest. And so, having started this in Dublin, when I came to do my academic position in Loughborough, one of the things that I was really interested in doing was to play around with the surface chemistry. And I was lucky enough to have worked for two geniuses in the past. Damien and Rob had started as an undergraduate with Damien doing a project looking at silver ion transfer. I did my PhD with Rob, looking at the growth and movement of metal ions across interfaces, growing nanoparticles at interfaces. And so, inspired by these two guys, when I came to do it, I wanted to play around with the surface chemistry and play around with the functionalization and the composition and the makeup of these magnetic particles. And the cartoon schematic of what I had in my mind to do this is here, in that I wanted to create a droplet. Those droplets would then act as an interface to be able to not only encapsulate iron oxide particles within them, but to be able to be a loci for a specific interfacial chemical reaction, so that I could control the reaction that took place on the outside, and it would end up encapsulating something that we put on the inside of the droplet. And so I was trying to combine those two, if you like, parts of my life and career, where we were making these magnetic particles within the droplet, but then I wanted to apply some of that interfacial particle chemistry that we'd come across earlier on. And so the cartoon schematic of this, as I say, was that I could tune this. We could have a shell chemistry where I would be able to grow materials and grow a metallic skin, and as well as then fill it with any inner filling that I wanted to. And the examples I'll talk about today are iron oxide nanoparticles in there. And so that was the concept. And I was fortunate enough to have Sushanish work and come and study a PhD with me. So Nikita, as she often is preferred to be called in our group, set about, if you like, working on this vision. I'd managed to convince her that this was a good project, that this would be a really cool thing to do. And the starting point was to look at some gold chemistry, and just to look at what we call shell chemistry. So we're not going to fill anything in the middle of the organic droplet now. We're going to have some reductant in the organic phase. We'll have metal ions on the outside, in this case gold, and we'll let that reaction take place. And just so that we're clear in the way that we set this up, we have P2 here is continuous phase, it's water, and we're making hexane droplets, which is P1. And so the hexane comes out through this channel it makes these droplets. You can see all the individual emulsion droplets. At this point, this liquid here is aqueous, but it doesn't contain any metal ions. What we do is we generate the droplets. These are our little chemical reactors. These are our little capsules of hexaferrocyanide and, decamethylferrocene. These are our little packets of decamethylferrocene, and we let those droplets go out into a beaker that contains then metal ions that we stir. And that's when the reaction takes place. And so the reaction isn't taking place here in this example that I'm going through. So we made these droplets, and Nikita went off and imaged the products. So it was clear that we were making materials. When we were doing this, we could see the color changes, we could see particulates, we could collect them. And Nikita kept going down to the SEM, and more times than I would care to admit, would come back with me with images like this, and I would say, well, it's fantastic, it looks really interesting, but it's not what I imagined. I was picturing, I don't know spherical particles or something that looked like a sphere. And I kept trying to convince her that maybe she hadn't washed the imaging stuff well enough, or there was something else on there, because as you do, you get set in your ways, you have this specific vision of what you thought was going to happen, and it wasn't that. And then she eventually managed to convince me. She's very patient and didn't use too many horrible words in trying to convince me in this, that I was not right and that this was actually gold. And we'd done the elemental analysis, and what actually was happening was we were making these wonderfully large platelets of gold via this process, and it was completely unexpected. And not only was we making these platelets, but it turned out what we made, i.e. the shapes and the sizes, was dependent upon the droplet size. And so we can tune the size of these droplets very easy by changing the flow rates or the ratios between these flow rates in the system. And we initially had thought about changing reactant ratios and adding other stabilizing or inhibiting molecules into the liquid to try and stop certain crystal planes growing. And before we even got anywhere like that, it turns out by just taking the same reaction but taking droplets of different sizes, you ended up getting spherical gold particles all the way up to platelets. And it was incredibly reproducible. It wasn't always perfect. So you can see there are some smaller spherical particles amongst these bigger platelets in this. But it was incredibly interesting to find that we could really tune the morphology and the shapes of these by just simply changing the droplet size. We hadn't even gone on to any fancy chemistry yet by adding ligands in there, and we were getting wonderfully different particles. Those platelets of gold were wonderfully crystalline, and in some cases when we put them under the TEM would simply dissolve and melt away. They're only 90 nanometers thick, but microns in size, single crystals. And you can really make quite a lot of these. And one of the projects we had going on just before we were shut out of the lab with the lockdown was to start putting these onto electrode surfaces and to see if we could see any other different types of chemistry on those, which we haven't got through to yet. But they're really, you can make quite a reasonable amount for these in doing it. But it wasn't what I initially would set out to. What I wanted to try do was to make a magnetic inner phase and a gold shell, inspired by some of the work using gold shells for imaging and analysis. But we did try to do that process anyway, regardless of what was happening with the gold, by adding some iron oxide particles in there. It didn't change the chemistry. So the gold still made the same products, but we were able to at least coat those gold with iron oxide. So all of those particles that you can see in those images have been extracted via handheld magnets. They've got the iron oxide on the outside. You can efficiently remove your product from your reaction pot, but it wasn't that core shell process that we had going on. And so this was really the first insight. And if we're honest, when we were writing this, I didn't really have a really good feel for the mechanism. And I guess you could argue I probably still don't, but it's wonderfully interesting and it drives us on to do more stuff. And, you know, it was clear at this point that this wasn't a simple reaction of a droplet making metals. And so we pushed on, and this is where we were drawing on now. I was really just taking some of those reactions that I'd done with Damien and Rob earlier on. We thought, well, let's just substitute the metal. It's not, whilst the gold is really interesting, I wonder if something else would work a bit simpler for me. And we tried some palladium and we tried some silver. So here's that same shell chemistry now for 2 different metals. We haven't changed anything else. We kept the droplets the same. We've kept the electron donor the same. And this is kind of what I expected to see in the first case. If I'm honest, this was something that kind of looks like a droplet. Now the solvent has gone. You can see it resembles something that might have come from a droplet. And in my mind, I thought, well, maybe this is something like a Pickering emulsion. We've made metal particles on the outside of the droplet. We've removed the solvent, and we can see the final material. And we got something for silver, and we got something for palladium. We thought, wow, fantastic, let's press on and keep going with this. And just to really show you, one of the things that we actually thought would happen for silver, because it has a very similar growing mechanisms or preferred crystal faces in gold, we actually expected silver to give us lots of platelets in some ways. And we didn't see as much. We did see some platelets with the silver, and it certainly was more crystalline when compared to the palladium. But the palladium particles were much more easy to fragment when you prepared them. So I show you this image here where the palladium particles look at like nice clusters. Actually, it really depends on how heavy-handed you are or how you handle them on the SEM stuff, because often they can shatter. And you see these clusters of smaller nanomaterials in there, which is reflected by the diffraction patterns of those. But we wanted to press on. We wanted to put the iron oxide in there. This was the first example of that with silver and iron oxide. And so you image these at the end of that process. We got these nice spherical particles. All of these have been extracted by a magnet, so we know they're magnetic. We know they've got iron oxide in there. But we noticed before we even started to do a lot of analysis on them that they're very polar dispersed in their size. When you make the emulsion droplets, in theory, they're very regular in the size of their that you make them, and it usually results in a very uniform iron oxide spherical particle. And so when you see something like this on your SEM stuff, it shows you that the particles, those emulsion droplets, weren't stable. During that reaction process, something's happened to destabilize it. You've got them coalescing, dropping out. I've got a wide range of sizes here. And not only were we getting, if you like, magnetic particles from a process when we had silver iron oxide, but we were getting a lot of nanomaterials within the liquid, which were silver. And so this is the diffraction pattern of those nanomaterials. And the elemental analysis tells us that they're silver. So we're making silver particles, but they're not staying with the droplet. Yeah, they're being shed into solution afterwards. And interesting to note that whereas before we had very nice diffraction patterns for the silver made in the absence of iron oxide, here we have something which is less crystalline in its nature on average. And so it tells us that they're different sizes and that reaction process is a little different. When we cut these open, okay, going back to my simplistic schematic, silver shell on the outside, iron oxide in the middle, you cut them open and you do the elemental analysis, and what you hope to observe is some sort of shell on the outside which is metallic. And what you're seeing in the images here is this is the SEM. And then as we go through the elements here, I've got iron and oxygen. That's throughout and continuous, so you would expect that. They're solid iron oxide. These are all clusters of nanomaterials. We're not seeing the resolution of the nanomaterials there, but they're all drawn together after the hexane and solvent has been evaporated. And the bottom picture here shows us where the silver is. And so the silver isn't on the outside as I expected it. It's in the liquid because it's been shed from the droplet, but it's also been encapsulated within the droplet. And even more confusing when we're comparing this with our gold platelets of beautiful sizes, and to find suddenly now silver is embedded within those iron oxide of those particles. And so it's clear when we were going through this that it wasn't a simple mechanism. And so this is a list of things that we were hypothesizing with Nikita, and I haven't even covered all of the components in here. You know, the concept that we have these droplets, that we have some metal in the outside continuous phase, the water, that is allowed to go on and react at the interface, if it is truly an interfacial reaction. In theory, this concentration is the easiest thing to control because it's in excess on the outside. And as I change the droplet size here, I change the concentration or the number of electrons potentially possible for the reaction to take place. But I change so many more things in a droplet. I've got the size of the droplet, so I've got the curvature of the interface, and then I've got diffusion to a concave or convex surface of different curvatures. I've got the solvent evaporating, forever changing the size of the droplet, and as you change the droplet size, you've got the movement of any iron oxide materials in there. That changes the viscosity and the composition of the droplet. You've got the reactants trying to then move through those iron oxide materials to get to the point where the reaction takes place. And then you've got the process of, is it a continuous nucleation? Is it instantaneous? What happens? And so it's so much more complicated than what we thought we were going to do. And to show you how it kind of even affected by the metal that we use, this is the equivalent example of palladium now, as what we showed you with the silver. All we've changed now is the metal in this. And I've got 3 examples going from A, B, and C. It starts off with the same droplet size. It starts off with the same reactant ratios between palladium and the electron donor. The only thing I've changed going from A to B to C is the number of iron oxide, the concentration of those iron oxides in there. Now, in theory, they don't take place or interact with that nucleation process. They just sit there. But you can see that as you change that concentration, the size and the morphology of those particles changes. It goes from a nice, if you like, it's not spherical, but it's a solid particle to something that looks like a wrinkled raisin. And again, we did a similar analysis. Here we've got the iron oxide, and the palladium parts of this are those white flecks on the inside. And I'm going to show us E and F in a bit more detail now on this slide. So again, from A to B here, all I've changed is the number of iron oxides in the emulsion droplet, and the reaction takes place, and you evaporate it, and you can see the cross section. You can see the iron, the oxygen, and the carbon of the ligands on the outside of those nanomaterials are well dispersed throughout, but the location of the palladium completely changes depending on what you do with this. And so how it's internalized, why it's internalized, is unclear to us. We're still trying to look for this. And in theory, the only thing I've changed from a whole range of list of potential possibilities is simply the way that the reactants could diffuse within the droplet to the growing metal particle. And that's changed what we've ended up with. Now, one of the thought processes for us is why it's so different from all of the different metals was the speed at which the metal grows and nucleates as it carries on. And in this example here on the right, we have the least amount of iron oxide. And so in theory, the decamethylferrocene is least hindered. It can get to the surface to react and form metal. And a hypothesis for us was, well, if that can happen really quickly, then maybe you can generate a metal skin. Those metal particles lock in place. You formed a continuous metallic shell on the outside of it. And so as the hexanes evaporate, it deflates that droplet and it looks like a wrinkled raisin here. But if that was purely just the case, I think you would see different examples in the silver, because what you're looking at on this side here is the time versus the absorbance, where we're following the speed of reaction between the metals and that electron donor. And they all proceed spontaneously, but they proceed at different speeds. And so what I've got in here is gold, which is this sort of light blue. I've got palladium, and silver is by far the fastest reaction taking place. So if it was just about making as much metal as you can, as quick as you can to form a stable shell, you might get different things. And now that's a very simplistic overview of the stability of particles at interfaces, but it was a driving thing. So it's clear from when we were doing this, and Nikita really was a fantastic student to mentor as we went through this. It was incredibly interesting to see what you thought would be a simple reaction turn out to be something way more complex. And we don't have, for sure, an understanding of all the mechanistic aspects of that. But what it's led us to do is to try and think about how we can study it in detail. And so whilst we're playing around with these different chemistries, and we have changed the different types of materials from titanium oxide to various different other metal oxides and metals in there. What we're also trying to work out is, can we create embedded sensors within those channels to allow us to really interrogate the reaction taking place. And so in other aspects of the group, we've been developing fluidic chips for characterizing analytical assays. And what we were hoping to do is to merge these two areas to allow us to understand the mechanism. So at the moment, what we're doing is we're doing a flow chip. We're making a material, we collect the product, and then we go off and do the analysis, right? And so what we really want to do is to be able to have some sort of chip with embedded sensors, very specific for the reactions that were taking place, that allows us to follow the reaction, to understand it, to allow us to feed back in real time and change the parameters and collect the data that comes out. And what we're working on at the moment is an in-between version, because what I don't want to do is to change the flow chip, the way in which we make the droplets. I wanted a sensor that I could couple into any existing commercially available flow chips that people use to make these emulsion droplets, to allow us to do the measurements and to follow it. And so what we've been working on is a series of different sensors that we can integrate into this. And we're not yet integrated everything together, but I wanted to talk through some of our process of making these sensors and what it means for coming back to droplets later on. So here was the concept. We wanted to be able to make our droplets. We wanted to embed. Ideally, what we were looking for was optical, electrochemical, and other measurements alongside that would work in tandem to look at these droplets that we're making, to verify what the droplet was, how big it was, what the reaction was taking place. And we wanted to do it in a way that was easy to fabricate. And part of that is because we're at Loughborough, and Loughborough at the time was having a big, I'm sure as similar as everywhere else, 3D printed phase where everything had to be 3D printed. That was cool and trendy. And so we weren't looking to use, to generate these sensors via typical lithography. We wanted to lean on the additive manufacturing processes that we had here at Loughborough. And so what I'm going to show you some examples are using SLA additive manufacturing, where you build up layer by layer the features of your fluidic chip and sensor by using a scanner to set and polymerize a resin. And you build up the features that we're going to go through. And by doing this, our concept was that we could then create bespoke combinations of sensors to bring to bear the measurements of our droplets and other analytical processes that we had going on. And so one of the first things we wanted to do was to put essentially a flow cytometer set up in our chips. We're making lots of emulsion droplets. What we wanted to do is to be able to line them out, thin them out if you like, so that only one or two of them ever pass through a sensing zone. And so to do that, what we're going to do is pass them through a sample inlet with two sheath flow carrier fluids that essentially dilute the emulsion droplets, spread them out and allow us to pass through a sensor. And we're going to demonstrate that process in the first instance by using an optical fiber optic sensor. And if you haven't come across doing a lot of 3D printing, let me just say that depending on how you fabricate your product in an SLA bed, it is the orientation in which you print, so you can get very different quality products at the outside. So this is the same type of device, but printed in different directions on the printer. And you get very different types of smooth features in your flow channels. Sometimes the software puts in support features just to aid the print that you're not even aware of, and it really disrupts the flow. And so you have to be careful in doing these optimizations for this. All of our printed devices in SLA, because we wanted to have small channels, needed to be printed on the surface. And so the small grooves that you can see here are actually all on the surface of this device. Okay, and that's because we can then get much narrower channels. We can get the resin, the unset resin, out of those channels much easier than embedding a flow channel deep within an SLA material. So we've got channels on the surface, which we then seal over with a piece of tape. We can put a fiber optic in there. We can then integrate these into our droplet reactors. And you can really control the size of that jet in a very simple, easy to make device. So you can go all the way from a couple of microns to a whole wide range of if you like, feed stream, those droplets coming through. And you get information, as you would expect, in terms of the absorbance, the different wavelengths. You can validate what the core strength is. And so we wanted to make sure that we could control the thickness and the number of droplets, but also get some other information. And so, yes, you can get optical measurements, but you can also get some information on the size of the droplet. And so I won't labor these points too much, but this is the time versus intensity. What you're watching there is the intensity of light. And every time a particle or a droplet sits in the way of that fiber optic, you see a decrease in intensity. And the magnitude of that decrease tells you something about the size of the droplet. And we were able to go through and just show that we could characterize these droplets as they came through in terms of their size. Optical was one feature, one tool that we wanted to bring to bear for this reaction. The other one was electrochemical processes. And so we wanted to put electrodes into these flow channels where we would flow the droplets through, and the electrodes would allow us to tell us something about it. As a test case to embedding electrodes into this, we went back to looking at resistive pulse sensing or Coulter counters, where you embed two electrodes and you apply a potential between them. That induces a current flow between these two electrodes. And every time a particle or droplet sits inside that narrow channel between them, you see a decrease in the current, and you can tell something about those particles. And so what you're looking at here is a baseline current that you would expect to see between these two. And every single one of these pulses is a particle that passes through a sensing zone in a microfluidic chip. And those pulses, as in the example of the optical case, tell you something about the droplet or particle that goes through. It tells you something about the particle volume, and it's very sensitive to particle volume. So if you take droplets that have a specific feature, or there are aggregates of those, you would see twice the volume. Okay, you wouldn't measure 2 microns in terms of the total size of the droplets. You would measure twice their volume. And of course, a cylinder of comparable features has a different volume. So in theory, you can resolve all of these out by this technique. And so you can tell about concentrations, you can tell about sizes. And this is that same example, using those same features where we embed channels on the surface of a chip. We have screw threads, so we can plumb the outlets of our fluidic chips straight into this, characterize the droplets that we're making, and then they pass back out and carry on the reaction. And so this was really, again, us demonstrating, starting to flex our muscles into how do we fabricate 3D printed devices in this. To get narrow channels in SLA devices, you have to print them on the surface, is what we found. And so as you make smaller and smaller features, you eventually lose the resolution. And there are 3D printing processes that will print nanometer size features. We were keen to explore this in an SLA printer that anyone could buy. Could we hack, if you like, an off-the-bench, easy-to-use 3D printer and have high precision resolution in terms of sensing methodologies without relying on those more complex additive manufacturing processes and instruments? And so what you're looking at here is our typical SLA printer that as you try to print smaller and smaller channels, eventually it just can't do it. It will not print features smaller than this. And when it comes to counting droplets and nanoparticles, size is key, because in resistive pulse sensing experiments, your channel, your sensing zone here, has to be about an order of magnitude within the material that you wish to characterize. And so if you're printing something about 50 microns in size, you might be able to characterize 5 micron droplets, but nothing of any smaller. And so the idea is to try and get it small as you can. But for now, in this process, we were stuck at 50 microns. And so as you make those 3D printed resistive pulse sensors, you can change the flow rate. You can look at how many droplets pass through per second. You can calculate the concentration and number of droplets you're making. You get a measure of the speed at which they go through, so you can measure flow rates. You can characterize their size, as you would expect in those measurements. and they're very accurate for different sizes. So you can have droplets of different sizes within your system, and you can characterize them in that way. And so those were nice examples, and I'm coming to, if you like, the better combination of these, and I swear it has something to do with droplets where I started in a second. This was our first, if you like, attempt at this. This was work done by Sarah Hampson, who was the first PhD student of mine to look at 3D printed sensor devices. And they worked really easy to make, really easy to embed the electrodes and the optical fibers, and you could couple them very easily into those existing flow reactors and droplet reactors that we used. But as I've hinted at, or mentioned, that they had limited resolution. We couldn't make features incredibly small. They had to be on a surface, and both of those really meant that we couldn't measure really anything smaller than 10 microns. And so that, whilst that might be applicable for some emulsion droplets, it didn't really allow us to interrogate yet the smaller droplets and the other materials that we might be making. And so Marcus was the next PhD student that came in to look at this. And this was work that we just managed to get out while in lockdown, which talks about this, if you like, our second generation. So we're not changing the SLA process here. We still want to use a simple SLA printer, but we want to try and trick it so we get better resolution. Okay, and so we're still printing the same channels. This is still the same sensing region where the particles are flowing through, and as they pass through that channel, you can characterize them. And it's still about 100 microns in size. We're not printing small features. We wanted to trick the system. Could I assemble components together to get me a better sensitivity? And the way we got around this and started to trick it is that we had a lid, we had a PDMS gasket or rubber seal, and then we essentially forced them together. And as you force them together, some of that PDMS or rubber seal creeps into the channel. That sensing zone within the channel is smaller, and as such, your if you like, your resolution intensity goes up. You can measure smaller particles because the channel is small, and it's completely tunable. So changing the tension on those screws completely changes the types of materials and the sizes of the materials in which you can characterize. And that's great in a droplet reactor or when you characterize the materials, because that also means that if it starts to block, you can release the screws and allow things to go through. The real cheat for us in this was not just to use a flat lid, but to use a lid with a ridge on it, so that that ridge sat within the channel with the same PDMS layer, that you would then increase the tension of the screws, and that ridge would creep into the channel. And if you increase the tension of the screws enough, you can effectively block it. It becomes a valve and shuts off the sensor. But as you change the screw tension, you can change the size of that flow channel and change the sensitivity. And then so with a simple SLA printer that's printing 100 micron features, you can start to measure particles and emulsion droplets all the way down to 2 microns in size. And that pushes it into a different realm. Now we can measure the smaller droplets, but also measure things like bacteria in other examples of the analytical processes that we look at. To give you a feel for how we could use this in droplets, what we also did with this sensor was to not just put solid spherical particles through, but other types of materials. And this gives you a feel for some of the benefits of resistive pulse sensing. You're measuring typically current versus time in the resistive pulse experiment. And the resistive pulse says that as a particle sits in the sensing region, it blocks some of the other surrounding buffer, and the sensor sees an increase in resistance. It blocks the current, you see a decrease in current, and that's what all of these resistive pulses are. But depending on the material that you put in, if, for example, is highly porous and it has a diffuse double layer or a large amount of electrolyte with it, or if the material itself is conductive relative to the surrounding solution, you don't get resistive pulses, you actually get conductive pulses. So an example is when you're looking at hydrogels that have a higher conductivity because they're loaded with ions and drugs. You don't see the resistive pulses, you see the conductive pulses, and you get an inherent different signal depending on their physical properties. And it's that extra combination that we're looking to bring to bear for this. So I swear I'm going to get back to droplets in a second, but this is where we got to then. We went through this whole process of designing flow reactors to help us look at droplet chemistry, to try and understand the reaction mechanisms. And we completely got distracted because we were designing flow reactors, 3D printed sensors that we could start to integrate different sensing technologies together. And so this is where we ended up. We've got a flow reactor where you can flow your particles or products in. It goes through a series of channels and out the other side. And what I've been showing you is sensor one, a way of characterizing particles using resistive pulse sensing. What we've also now embedded in here are different sensors, and then we can tune those sensors for different properties, whether it be optical or particle sizing, all the way down to tens of nanometers up to tens of microns. And so we're really measuring a wide range of particle sizes all at the same time in what we've been doing. And so rather than bringing this to bear on emulsion droplets today, we got way distracted, and we're now in the process of trying to commercialize some of these technologies for different applications. But we're just about getting through that. And I think we're about to come back to look at embedding these for droplets and using it for that chemistry. If I just talk about what could be possible, and I'll show you some examples of data now for sensor 2. So we can characterize the droplets really easy in sensor 1. We can see the size of the droplet. We can count how many droplets we're going we make during the process. What could we do with embedded flow? And there are embedded sensors along the channel that we could do different things with. Okay, and so I could just count particles as they come past, and I could tune those sensors for different size ranges. So if I'm making large emulsion droplets that are shedding silver particles or shedding other smaller droplets at the same time, I can tune these counters to tell me something about those. I could specifically trap some of those particles that are being made within that second sensor. So if I'm drawing up components of the bulk liquid, I could subsample. I can now actually start to extract specific types of particles and particle sizes into these materials as they go through. And we've been demonstrating that with polymer particles, where not only do we enhance the capture rate by varying the flow of these sensors as they go along the channel, but we can also block it, turn it off, and extract it. And so in the examples that we've been doing over the summer, and again, we got distracted from droplets. We were looking at COVID, where you'd be able to put samples in here, you would count the number of COVID particles, but also then you would be able to capture certain numbers of COVID particles, and you would extract those sensor bits to go off for post-analysis. But when it comes back to the droplets that we've got, we can extract droplets at different time periods along that flow channel and ask how is the reaction changed at different timescales. And so not only monitor the size of the droplets or the size of the materials, but subsample at different time zones as it goes along. And so we've been, we kind of started doing this because it's cool and I like it and it's fun to do interfacial product materials from going back to the PhD. And, it makes me feel like, I'm young again, playing around with metals being made at interfaces. What we really then realized is that we needed to develop some way of doing the measurements in a much better controlled scenario so we can understand the reaction, because this is way too complicated. What it led to was a really fantastic sensor that allows you to characterize particulates as they go through. And, we're hoping to bring it back to this now, so we can embed these different types of sensors. We can do the magnetic extraction, we can subsample and really study the mechanism. And so that's where we go. And I wanted to give you a feel for what we've done, some of the other processes that we've been going on in terms of developing with the sensors, but also where we're going. But this is really subject to me praying to the grant funding gods, because I'm hoping that we get some money to allow this to take place now. Now we've put the time in to develop this so that we can really understand and go on to develop some of those nice core shell or combinations of particles. So listen, I really appreciate your time. Marcus and Sarah have done a lot of the 3D printed chemical sensors. Nikita Sushanushachdev did all of the droplet work that I've shown you. And I'm very grateful for those people that have sort of supported us and funded us along the way. And I'm very grateful and thankful for your time and for being invited to come and do this.
Amazing. Thanks, Mark. It looks like so much fun. I really want to play with that sensor. It's brilliant. It's so multifunctional, and I think you're only limited by your imagination in what you can put in there, you know. So it's great. I think there'll be a lot of questions on this. So any questions now from the crowd?